Okay, so today we are talking about bivariate quantitative data. What does bivariate mean? Two variables. Very good. Bi means two. Bivariate is two variable quantitative. So we are looking at paired quantitative data, generally two numbers that came from the same source, and we're looking for a relationship between those two quantitative variables. Good. If those two variables have a vaguely linear relationship, we can model them with a line of best fit, also known as a least squares regression line. Sorry, I'm fine. I'm just dying a little bit. It's okay. It's nice to know my cough drop's working well. We've seen this with our sample regression line. Y hat equals a plus bx. It's not funny. I feel good. And you guys told me earlier y hat is our predicted, a is our y-intercept, and b is our slope. Thank you for being patient with me. The sample regression line is related to our population regression line with some changes. So instead of y hat, a predicted y, we're actually looking at the mean of all of the possible y values for a population value. Because I know, for example, if I was looking at the population data for height versus shoe size for Rancho San Juan students, that for any given height, I'm going to have a spread of shoe sizes, right? If we looked at our class data for people who were 5'4", we had a wide variety of shoe sizes. So this is the mean of all of those y values for any given x value. So y, the mean of the y's is equal to alpha plus beta x. And some of you may recognize those symbols. We saw alpha and beta when we did significance testing. Alpha was a type 1 error. Beta was a type 2 error. That is not what they mean here. Alpha is the population y-intercept. Beta is the population slope. So we have some overlap in symbols. We're going to have to use context to help us sort out which one's which. Dude, I hate allergies. Allergies suck. The mu sub y is then the mean of the y values for any given x. We know that if we want to do inference for a statistical quantity, the first thing we do is build a sampling distribution for that quantity. So in unit 6, when we talked about proportions, the first thing we did was look at a sampling distribution of proportions, all possible sample proportions. We did the same thing in unit 7 for means, the distribution of all possible means. We're going to do the same thing here, but now for sample slopes, because we're interested in doing inference about the population slope, that relationship between x and y. So we're going to build, just grab them. No, walk up to them and talk to them. Don't interrupt my lesson. Who are you looking for? Oh, yeah. So we're going to pick a sample size of, let's say, 30. We're going to collect all possible samples of 30 and look at the sample slopes for those samples of size 30. And that should produce a sampling distribution of sample slopes, just like we did for means and proportions. And just like for means and proportions, we have some rules that guide what those distributions look like. So for a sampling distribution of sample slopes, the shape is approximately normal. And you seem a lot less excited about that than my second period. We are back on familiar ground. Yeah? This is going to be a nice, pretty symmetric bell curve, just like we saw for proportions and means. Yeah. The mean of my distribution of sample slopes B, so mu sub B, is equal to the population slope, beta. Just like the mean of my sample means was equal to the population mean. And the mean of my sample proportions was equal to the population proportion. Same idea. The mean of the sample slopes should be the population slope. Now for the less pretty part. The standard deviation, sigma b, is an ugly fraction. Dude. Did anybody eat anything that had nuts in it today? Something in here is triggering my allergies big time. Whew. Sigma b over sigma x times square root of n. My hope is that looks vaguely familiar. We've seen sigma over square root of n before. We saw that with means when we were dealing with one variable quantitative data. This one's modified a little bit. There are two sigmas now floating around. The one on the top, the one in the numerator, is the standard deviation of residuals. Do we remember what residuals are? Oh. That was adorable. We need more of that. Actual minus predicted. Actual minus predicted. The residual is how far our value is from where we expect it to be. Actual minus predicted. And I expect for every y value, there's going to be a residual. This is the standard deviation of those residuals. Sigma x is the standard deviation of the x values. So in our warm-up activity, it would be the standard deviation of the heights, which was our x or our input. And you're probably thinking, OMG, I don't want to have to calculate that every time I go to build a confidence interval or do a significance test. And the answer is you won't have to, because sigma b is given in the computer output. We remember those computer output tables from Unit 2 that we use for linear regression. We're going to see them again. Sigma b is one of those values that the computer output gives you. You're never going to have to calculate this by hand. It will be given to you. You just need to know where to look for it. So yes, the equation is ugly. No, you don't ever have to use it. Yeah. And then n is the sample size. This is important that it is the number of people you collected data from, not the number of numbers. Because I have two sets of numbers. I don't want to double count. So for us, we should have had 29 pairs because there were 29 people in the room. My sample size is 29, not 58. I'm sorry. I'm sorry. You're all looking at me like I'm sad and pitiful. I'm sorry. Who's next? We know who the popular people are. All right. We're going to do two things in Unit 9. We have two types of inference. One is estimating something we don't know. So we're going to estimate a population slope based on the sample slope. That's a confidence interval for beta. So we'll collect some sample data, we'll calculate the slope of the regression line for that sample, we'll use it to build an interval that estimates the population slope. The other thing is I can test claims about the relationship between two quantitative variables using a significance test for the slope. So this looks like that test for independence for categorical variables, similar idea. I am looking at whether two variables are related by testing claims about a slope. If the slope is 0, there is no relationship because as x is changing, y is not doing anything. If I do have a positive or negative slope, then there is a relationship. As x changes, y changes in response. So that's why we're building things for slope when we're actually talking about relationships. Slope is an indicator of whether there is or is not that linear relationship. We're going to start with intervals. We already know how to build them. Sample statistic plus or minus margin of error, yeah? And we know that looks like sample statistic plus or minus critical value times standard error. That same formula works for these intervals. We're going to start by working through the process. We know the state part. We define our variable. Here, we are building confidence intervals for beta. So I would define beta in the state step as the true slope between, and then I would state my variables. So for our example in class, I would state that beta is the true slope between height in inches and shoe size and US women's sizing. I would state my confidence level because we know it's a confidence interval. And then I would move on to the next step. What comes after the state step? Plan. What do we do in the plan step? We check the conditions. Up to now, we have had 3 of them. They've looked the same. I know. Deep breath. The conditions we've been checking are up there. They just look a little different. If I can stop coughing, we'll go over them. Okay, so first we'll start with the familiar ones. This second bullet point is independent. I want my sample selections to be independent. Yeah? And we check that by either checking that we're sampling with replacement, or how do I check for independence? 10% condition. So we already know how to do that. That is not a problem, right? The condition down at the bottom, we can guess what that is. That's our random check, right? We've done that before. Random assignment or random sampling. There's one more we've done up there, which is the middle one. That one is normal. When x is fixed, y follows a normal distribution. Meaning for any given height, the shoe sizes are normally distributed. That's a little weird. We check that by using our calculator to make a histogram of the residuals. You will notice that, yes, you may. You will notice that in your homework, in your book, they often do this for you. You'll see a whole bunch of graphs given to you for these problems. So the focus for us really isn't on making the graphs, it's just knowing what to look for. Remember that when we're checking graphs for normality, we're making sure there are no outliers. We're making sure there's no strong skewness. So you would create the histogram on your calculator, or you would be given one, and you're just going to state no outliers, no strong skewness. Yay. So those three should feel vaguely familiar. It's the two new ones we have to talk about. The first one is a linear check. We are talking about linear regression. Slope usually talks about lines. Lines have constant slope. So we are looking to make sure that when we graph our sample data, X and Y look vaguely linear. So we are going to check a scatter plot of X versus Y. The scatter plot of X versus Y should look vaguely linear if you hold it and you kind of cross your eyes and look at the blurred out version. Not perfectly linear, but vaguely tilting, either positive or negative when you look at it. Again, most of the problems in the book are going to give you that scatter plot pre-constructed. If not, use your calculator to generate it. Don't take time to do it by hand. Sorry. This one down here, the last one we haven't talked about, is equal SD. What does SD stand for? Standard deviation. So we want to check that the standard deviation of the residuals does not depend on X. The standard deviation of the residuals should be independent of my input values. So we are going to make what's called a residuals plot. Which is X versus the resids. It is a scatter plot of X versus resids instead of X versus Y. That's a residuals plot. And we are checking for a pattern. We should not see one. It should be random. We want random scatter. If you see fanning, starts out small, gets wide, or starts out wide, gets small, or has a very clear curve, this is a no-go. That is bad. We do not want patterns here. We want random scatter. There is a blank I missed in my coughing fit that nobody called me on. In the normal, said check a histogram. There's an exception. If my sample size is bigger than what? 30, I don't care about the graph. Yeah. So if I have a big enough sample size, I don't have to look at the graph. My sample size is 30 or over, doesn't matter what the graph looks like. My sampling distribution will be normal. Central limit theorem still applies for numeric data. Good. We listed in this order because they spell out something we can remember. Liner. Like eyeliner. Yes? Yay. Linear, independent, normal, equal SD, random. Liner. Yeah? After we do our checks, we checked all 5 conditions. What comes after the check stage? The do stage, we build our confidence interval. And it looks like it did before. It is a sample statistic, B, plus or minus a critical value, T star, times the standard error, SB. Not terribly scary. We know that T star is our critical value. For the student T distribution, which is a bell-shaped curve that looks kind of normal, but it's wider than the standard normal. And it has a degrees of freedom. Up to now, we've used n-1 because we were looking at univariate data. We are now looking at bivariate data. This is going to be n-2. Yeah. Maybe, if my pen would cooperate. The world does not like me today. The standard error, SB, You'll notice this looks a little bit different than how we defined it for the sampling distribution. The sampling distribution was looking at population standard deviations, and it was square root of n. This is pulling sample standard deviations, and it's square root of n minus 1. And we saw that same change when we talked about standard deviation way back in Unit 1. When you switch from population to sample, you go from root n to root n minus 1. Again, you shouldn't have to calculate it because this is in the computer output. You should not need to calculate SB. That should be given to you in the computer output. B should also be given in the computer output, meaning the only thing that I have to calculate to set up my confidence intervals is my critical value. How do I find critical value? Inverse T, yeah. We already know how to do it. It's the same as the means and proportions. Yeah, good. Good. Not so scary. After we do the do, we do the conclude, which is our sentence frames. And they are the same as every other confidence interval we've done this year. We are blank % confident that the interval from blank to blank captures the true slope between variable 1 and variable 2 in context. Same sentence frame we've been using for every other confidence interval. When it comes to taking that confidence interval and using it to support a conclusion, if the interval contains 0, we do not have evidence of a linear relationship because the slope of 0 is a plausible value, and the slope of 0 means as x changes, y is not responding, meaning no relationship. If my interval does not contain 0, we do have evidence of a linear relationship. As x changes, y is responding by either increasing for a positive relationship or decreasing for a negative relationship. And that is the same rule that we were using for two means and two proportion tests. If 0 is in the interval, no evidence. 0 is not contained is evidence. Same idea. We're going to start with some examples. We'll finish examples on Friday, next time I see you. I see some nodding. Yay. Okay, my voice is killing me. Do I have a volunteer who would be willing to read example 1? Thank you, Katie.
Cars and trucks use value from where they are driven. Can we predict the price of a used Ford F-150 Super Cruise 4x4 if we know how many miles it has on the odometer? A random sample of 16 used Ford F-150 Super Cruise 4x4s was selected from among those listed for sale on AutoTrader.com. The number of miles driven and price in dollars were recorded for each of the trucks. Here are the data. Construct and interpret a 90% confidence interval for the slope of the population regression line.
Very good. Thank you. So, first question. What are we being asked to do? Confidence interval. Yeah, very good. So, confidence interval, they were nice. They gave us a confidence level of 90%. And then the big important thing is for the slope of the LSRL, for the population of the slope. So it's a CI for a slope. CI for a slope. We are going to assume for the purposes of this problem that the conditions have been met, and we're going to jump straight to the do because I want to focus on what that computer output's telling us. So I'm going to scooch you up. I know that for my CI, my formula is B plus or minus T star times S sub B, my standard error for sampling distribution of sample slopes. B plus or minus T star times SB. Two of those pieces are in the computer output. So I'm going to go back to our computer output and start looking at what's in there. So all of the computer output that you see on the AP test day will be structured like this table here. This looks like the output from a program called Minitab, which is very commonly used for statistical analysis. So the constant row has to do with my y-intercept. The variable row, which should have a variable label, in this case miles driven, has to do with my slope. And you will notice in that first column, it just says coefficient. So this first number here, that is my y-intercept. A equals 38,257. That's my y-intercept. This second number here is my slope. My sample slope is negative 0.16292. Yay. The second column, what is the title of the second column? Standard error, SE coefficient. Yeah, we know that this means standard error. So this number here is SA, which we're never going to use. This number here is my SB. And you will notice that's what I need for my confidence interval. So everything I need for this interval is in that second row. Here is my B, here is my SB. They are giving me the information. You will notice we're never going to touch these four for confidence intervals. Those have to do with something else, which we'll talk about next week. Not next week, week after next. R-squared adjusted, we're never going to use. There are two more variables up there we haven't defined, numbers we haven't defined. S. Anybody remember what that S is? It's a standard deviation of residuals, yeah. Otherwise, it would have a subscript, yeah. That S is the standard deviation of residuals. And this is what it sounds like. This is R squared, my coefficient of determination. So my coefficient of determination is 0.664. If I wanted my R, my correlation coefficient, I would take a square root of 0.664. Good. I only need the two I circled in blue, as those are the ones we're going to use to build our confidence interval. So sample slope minus 0.16292 plus or minus, I'm going to leave a space for my critical value, times, and then I'm going to copy my standard error, 0.03096. To get my confidence, or not my confidence, sorry, my critical value, I need to look at the t-distribution. It's still recording, so no, we're not going to panic. Happy thoughts, happy thoughts. Come on. There we go. Good job. So we're going to draw our student t-distribution. Nice, pretty symmetric, roughly bell-shaped, 0 in the middle, 3 standard deviations out on either side. Bless you. I sympathize. And then we are going to put our confidence level in the middle of that curve. I want to block off the middle 90%. I have a sneaking suspicion that's going to be just inside of 2 standard deviations. I know my critical values, plus and minus, then form the boundaries of that middle 90%. In order to find my t-star, I need 2 things. First, I know inverse t wants the area to the left. So if 90% is in the middle, how much is left for the tails? 0.05. 5 and 5. 10 total. cut in half because it's symmetric. So 0.05. I need degrees of freedom. How many data points are in that data table? 16. 16 minus 2 is 14. So that's going to give us a T star of, I don't know, because I haven't done this in a while. What did I get for a T star? 1.761? Yes? Yes, good. I'm going to take that value. I'm going to go substitute it in up here. 1.761. I'm going to give you just a second to use that formula to calculate the boundaries for our confidence interval. Try it manually. What do we get? What do we get? Yes, you may. Okay. When I did it, I got, what did I get? I got negative 0.217 and negative 0.108 rounded to 3 places. Yes. Yay. Good. Very good. And calculating these manually isn't too bad because they're giving us B and SB. That's not too scary. There is a way to do this by putting the data in your calculator. So if I wanted to do this with my calculator to check and make sure I did it correctly, you would start, I can contain my thought here, by putting the X values in list 1 and the Y values into list 2. We want to make sure we do it in that order. And then you are going to go stat tests. And you're going to go all the way down to the bottom. And I have to check what letter it is. G on mine. And it says lin reg t int. Lin reg t int. And lin reg t int is going to ask you where you put your X and Y values. It's going to ask you for frequency, which should stay 1. Don't touch that frequency number. It's going to ask you for a confidence level, 0.9. And then you would run that command on your list of data, and it would spit out exactly that, because I ran it this morning with my second period. So if you want to check data in the calculator, lin reg t int. Because we're getting so much information out of the computer output, these I usually find faster to do manually just from what I wrote on my paper. I think that the calculator adds time instead of subtracting time when they give me computer output and graphs. If the AP board is in a cranky mood and they don't give you graphs and you have to construct those scatter plots and residual plots and histograms on your own, then it's worth putting the data in the calculator, because you're going to need that data in the calculator to build the graphs and run the t-int. So in that instance where they didn't give you graphs, your calculator is faster. If they give you graphs and computer output, you can bypass a lot of the calculator math and just do it by hand. Okay. So, yeah, I was going to ask. We got about a half an hour of class time left. We have 2 more examples. What I'd like to do is give you some work time today so that you can finish the quiz if it's not done, finish the Unit 8 review if it's not done, get started on your 9A homework, and then we'll finish our examples together on Friday. Reasonable? Yeah? If you have questions, let me know. Please use the rest of class times wisely. If you finish your Unit 8 quiz, you could turn it in before you leave today. Drop it in my red inbox. Reminders that those assignments, Unit 8 quiz, Unit 8 review, are due on Friday. Friday.